Hey everyone, I'm having a technological issue here. My screen that I write on for some reason is not working, and I can't figure out why. It was working and then all of a sudden it just stopped working.
Is it connected by wires or wirelessly?
Oh, it's hardwired.
It's hard. Oh,
Yeah. Oh, wait, there it goes. Okay, I think I got it. This is weird. I had to reinitialize. I had to unplug the USB. I restarted the whole computer. It still didn't know what it was doing. Okay, let me share my screen. My mouse is acting weird as well. Okay, I think I'm good. In just a second, I need a new battery. Everything was going so good this morning. I don't know what happened. Okay, y'all can see my screen okay?
Yeah.
All right, any questions before we get started today? Audrey, the answer is yes, of course. Okay. All right, so today we're going to get into partial fractions, and then that's what we're going to do also on Wednesday. So lots to do here today. Let me open up. I've got a few things I got to reopen some programs here, so give me a moment. Okay. And there it is. All right. So this is our this is our last section when it comes to the different I guess techniques in terms of finding antiderivatives, right? Last section was all about trig integrals and making that trigonometric substitution. And now the last topic is this thing called partial fractions. And I told you we first have to get through a bunch of stuff first before we can even start this section. So the preliminary things we need to know, your formula sheet has formula number 17. This is an important formula. We're going to need to know how to use it. And I want to show you how we've seen it, but there's a slight little difference here in this formula. The thing that we've done is if we had something like, integral 1 over x squared plus 1 dx, something like that, we all should have just recognized this as being the antiderivative being arctangent of x plus c, right? That's something that we talked about that, weeks ago. But now we're going to make a slight little change to this, and that's we don't need a 1 here, okay? That can be any number. And then this formula applies. So I'll show you how that would work. If we had integral 1 over, let's say, x squared plus 9 dx, then that would be, well, here, the 9 is the a squared. So a would be 3 here, and then we just use this formula. So it'd be 1/3 inverse tangent of x over 3 plus c. Y'all see how that formula works? And they're using u in the formula instead of x. For the integrals I just showed you, it's x, right? And then it doesn't have to be a perfect square either, right? If this is 1 over x squared plus, let's say, 5 dx, well, then a is the square root of 5, which is just square root of 5. So I would put 1 over square root of 5 inverse tangent of x over root 5 plus c. All right. So that's how we handle, pretty much now we can handle anytime we see our variable squared plus, okay, plus a number. Right now, if it's a minus, it's a different story, all right? But if it's a plus between them, then we can use this formula. That's the first thing that we need. Then we have 8 different integrals I'm about to do with you. Okay, there's 8 different integrals that all have certain aspects to them that we need to be able to recognize and then know how to handle them. And we're going to start with easy ones and get harder. So the first one we all need to be comfortable with is if we ever see a constant, that would be a number like, 2 or 5 or -10, doesn't matter, any constant divided by a linear expression in the variable we're talking about here. So if you look at the denominator here, x minus 4, well, that's a linear expression. And then on top, we have a constant. Anytime we have this, it's just a simple u substitution, right? I mean, I'm going to show you the u substitution on this one, but moving along, we're not going to want to have to do the u substitution each time. The u here would be just the bottom, x minus 4. Du would just be dx. And so this integral could be rewritten as 2 over u du. That's just basic u substitution, right? The first type of substitution we learned. And then you can pull the 2 out, 1 over u du, and the antiderivative of that's natural log. So I'd say 2 natural log absolute value of u plus c. And then that would be 2 natural log of u, which was x minus 4 plus c. Make sense? What we want to be able to do is go directly from here to that answer without doing any work written down. We need to be able to look at that and go, oh yeah, okay. U is the x minus 4, du is dx. Okay, it's going to be 2 over u. Antiderivative is 2 natural log u, right? Let's look at a slightly different one. Any questions there? Slightly different one here. Still have a constant on top, right? Still have a linear expression on the bottom, but notice on the linear expression, we have a -5 in front of the x. And that's going to change things a little bit, because if we did our u substitution here, 4 minus 5x, the linear expression, the du is -5 dx, because that we're going to have to take derivative of -5x. And then we have to scale it. So we have to divide both sides by -5, or if you'd like, you can say you multiply both sides by -1/5. And then this integral will become the -1/5 that can come out, the 2 that was on top, u, and then du. And then again, you can pull the 2 out, do the antiderivative. You should get something like 2 times -1/5 natural log of 4 minus 5x plus c. The key here is this. We have to scale this out. Because we had a -1/5 in front, we're going to have to scale that answer by -1/5. If that was, let's say the integral was...
Question, how did that 2 get on top of the u?
Sorry, I thought I had
Yeah,
a
it
2
was,
up there. I apologize.
yeah.
Sorry, I just realized that when I looked up there. There is no 2. There's a 1. I thought there was a 2 from the previous problem. So there is no 2 there. So we have to scale that. So if we had something like this, let's say 4 plus 8x dx, something like that, then I'd say, oh, it's a constant over linear, right? So I know the antiderivative is going to be natural log, but because there's a +8 in front, I'll have to scale. I'll have to do 1/8 natural log of 4 plus 8x plus c. Is that clear? So you shouldn't be showing work for these when you get, because it'll just take too long to have to do all that. Okay, constant over linear, we're good. Let's go to the next type. A constant over a repeated linear. Okay, well, what do I mean? Well, we have our constant on top, right? Here we have a linear expression, 2x plus 1, but it's repeated, right? Meaning that it's squared. And so it's the same exact story as before, all right? It's the same story in terms of we would make a basic u substitution, But the key is that the antiderivative would no longer be natural log, would it? Because you would have 1 over u squared instead. And we still have to scale by the 2 that's in front. So does anyone want to give me an idea of, can anyone tell me what the antiderivative of this is without working it out by hand? Think about what it is, right? It's going to be 1 over u squared, right? But we have to scale it. What do you think?
I'm probably wrong, but it's probably I would say probably 4 times 2x plus 1.
4 times 2x. Not sure where you're getting. I think you're trying to take a derivative.
Wouldn't it be negative 1/2 times u to the power of -1?
Say it again. It'd be negative 1/2 u to the
Times
power
u
of
to the
negative 1.
-1.
Exactly. Okay, let me work this one out. Okay, maybe.
Why would it be a negative 1/2?
Let's work it out. So if you think about it, if u was the 2x plus 1, right? Then du would be 2 dx, right? And then you'd have to scale that. So you'd have 1/2 du equals dx. So let's rewrite the integral. It'd be integral 1 over u squared. And then we have 1/2 du. So I'll pull the 1/2 out. Any questions on that? Now we have to take the antiderivative of 1 over u squared. That's u to the -2 du, right? So when you apply your power rule, you add 1 to this. So this would become 1/2 times 1 over, I'm using the power rule. If I add 1 to that power, I get -1. So I have 1 over -1, u to the -1 plus c. And that's where we get that -1/2 from. -1/2, and then 2x plus 1, replace u to the -1 plus c. That would be an answer. That would be fine. You could also do it this way. You could write it 1 over, or negative, put the negative out front, 2 over 2x plus 1. You could drop the 2x plus 1 down on the bottom with the 2. So that's correct. That's correct. Make sense or no? Let's do another one of these. I'm going to make one up here. What if we had 3 over, see if I can make this weird. All right. So we have a constant on top. We have a linear expression on the bottom, right? But it's being repeated. So right away, I know I'm going to have to scale it by whatever that number is out in front of the x. I have to put that out front 1 over it, right? So I know my final answer will be -1 over 4. Understand? Now I'm thinking in my mind, I also have that 3. Let me put the 3 out there also, that 3 that's on top. But then I'm thinking, all right, when I do this, I'm going to get like a 1 over u to the 5th, right? 1 over u to the 5th, which is really something, and this is really like a u to the -5 that I'm integrating. And so I'm going to have to put a 1 over -4 u to the -4 plus c there.
Kind of like a shortcut,
I'm sorry?
kind of like an easy way
Yeah.
shortcut kind of do it.
It's
to
a
do it?
short,
Yeah.
we're trying
Okay.
to, we're trying to be able to do this mentally. Because if you have to do each of these, if you have to do each of these with this whole thing over here, you're going to run out of time on a test. And let me try and explain what I mean because of where we're headed. Okay. What we're headed to is doing partial fraction decomposition, where we take a very complicated expression and we break it into a bunch of easier expressions. And each of these, notice on this is a constant over linear, constant over linear, constant over linear, constant over linear, you know, constant over linear squared, right? So each of these is what I'm talking about right now. So if there's like 3 or 4 of them within a bigger problem, it's going to take you forever to get through the problem. Make sense? So we're trying to be efficient with the things that are easy to do. Okay, let's see here. There we go. Forgot to, yeah, there we go. That's what I was talking about. All right, let's get back to this. Where was I? We were in the middle of this one, right? So we've got all this. Let's multiply this all together. This will be equal to, we'll get a 3 on top, we'll get 16 on the bottom. A negative and negative is positive. U in this problem would have been the 1 minus 4x. That all would have been to the negative 4 power plus c. We could do that. Or if you wanted, you could write it this way. That would be just as well. Questions? I'll give you one more, okay? I'm gonna give you one more. See if you can do this one on your own. See if you can do it without writing anything down. Let's make that a -5 on top. Take a minute to see if you can get that one. I wouldn't expect you to just get like the final answer. You might need to write a few things down, but you shouldn't be doing the actual U substitution here. So if this were me doing this, this is the way I would do it. I would say, okay, I have this -5 on top. I need that. I have a -11 in front of the X. I need to scale that out. Okay. Then everything else pretty much just looks like I'm doing an integral of U to the -8. Right, that's really kind of what that's going to be. So the antiderivative of that's going to be 1 over -7 U to the -7. You know what? I don't need to put U there. Let's just do 4 minus 11x to the -7 plus c. And then the last thing to do would just be maybe put all those together. And that's it, right? So 5 over 77, 4 minus 11x to the -7 plus c. And of course, we could check our answer, right? We could take the derivative of this.
Is it -5?
Negative. Why did I forget the negative? Sorry, thank you. Yeah, we could take the derivative of this, right? Not going to, but we could check it. It would work, right? Okay. So recap. Well, formula 17 is a special case. All right. And then we have constant over linear is going to wind up having a natural log in there. We might have to scale it, right? We might have to scale it, but we'll still have a natural log, constant over linear. Now, constant over linear repeated, well, then we got to scale, we got to take account for the power rule. There's a little bit more involved there, right? But it can be done without a whole lot of work. Understand? Okay. The next thing, well, here, this was just another example. I think we can do that one pretty easily. You don't even have to scale because there's a 1 in front of the X, right? You should just be able to go straight to that. 1 over -2 U to the -2 plus C. So I was really just treating this like it was integral U to the -3. But I had no scaling to do. Well, scale with a 1. When you scale with a 1, nothing happens, right? Understand? Okay, that's it. Now we move on to the next type. What if you have, well, we did this one already. So what if you have a constant over a quadratic? Okay, notice we have a quadratic in the denominator, but the quadratic is missing the X term. We have no X term, all right? and we have a plus right here. Right, so constant on top, quadratic on the bottom with a plus in between, and we're missing the x term, right? We have an x squared term, we have a constant term, but we don't have an x term. You know what I mean by missing an x term? Like this is not x squared plus 2x plus 9. It's just x squared plus 9. There's no x to the first power anywhere in the bottom. It's just x squared. So this would be formula 17. So we just go right to it. 1/3 arctangent. I just did this one earlier. X over 3 plus c. Okay, formula 17. Okay. 3 more. A constant over an irreducible quadratic. All right, so constant on top. All right, great. Now the denominator is a quadratic and it has the x term. You see that 2x is in there, so we have the x term. If that 2x wasn't there, I'd be using formula 17. But because there's a 2x there, I need to look at it a different way. Now it's irreducible. Now, what do I mean by irreducible? What does that word irreducible really mean?
Can be reduced.
Can't factor it, okay? Can't factor. You know, like if I give you this, x squared plus 2x minus 15, well, that could factor. That could be x plus 5, x minus 3. That would be factorable, right? So that would be reducible. This is reducible. This is not reducible, all right? Oops. This one is not reducible. You can't factor that. So you can't break it into 2 pieces. So what do we do here, right? So this is kind of new. We haven't seen this really before. But what we're going to do for it, we have seen. We're going to complete the square. That's all we're going to do is complete the square. So we're going to take the denominator over here, x squared plus 2x plus 17, and we're going to complete the square. So we've done this. We did this last class, right? We're going to take the number that's in front of the x term here, take half of it, right? That gives us 1. And then we take that answer and we square it, which gives us 1 again. And that's the number, this number is the number that we're going to add and subtract, that hidden 0. So x squared plus 2x, here comes my adding of the 1 and subtracting of the 1. And then I still had the plus 17. Now by doing this, I'm guaranteed that the first 3 terms will factor to be x plus 1 squared. And remember I said that that plus 1 is actually from that first number. That will always be the number here. And then I still have minus 1 plus 17, which gives me plus 16. Now, when we do that and rewrite the problem, we get x plus 1 squared plus 16 dx. Anyone have an idea what I'm going to do now? Does that look familiar? If you kind of squint your eyes enough, does that look like something?
Yeah, you got a U sub.
You can do a U sub, right? And if you did a U sub, what would it look like after you're done with the U
The
sub?
antiderivative of tangent or arctangent, sorry.
Yeah, so this is going to wind up being formula 17. Do y'all see that? If you squint your eyes appropriately, this is like
U squared.
U squared, exactly. This is like a U squared plus A squared. That's what we have here. And the important thing to understand is that your U, right? This right here, if that was U, the derivative of it is just 1 dx, right? So there's nothing you have to scale. You would never have to scale because it's not ever going to turn out to be like 2 dx or 4 dx. It's just going to turn out to be 1 dx every time, which means I can go straight to formula 17. But instead of U, I'm going to use x plus 1. So this should be 1/4. Remember, a here is 4, right? A squared is that, which means a is 4. So the formula 17 is 1 over a inverse tangent of u over a. For us, what's u?
X plus 1.
X plus 1. So it'll be x plus 1 over 4 plus c.
That one's a nice one.
Yeah. Does that make sense?
Question, where does
Yeah.
formula 17 come from? Like, how do, it's an evolution of, well, we know the arctan's derivative, but
Yeah.
like how is that figured out there?
You could, well, we proved arctan's derivative, but if you wanted to prove this one, if you wanted to actually show that this is true, formula 17, the way you would do it, I mean, I'm not gonna have time to do it right now, but what you could do is you could rewrite the denominator here as the square root of this squared, okay? And then use trig sub. Because do you see you have the square root of variable squared plus constant squared? And so you go back to our, which one here, this one here, and we make a substitution. We replace our x here. For us, we have u, but we replace it with a tan theta. So you would basically go and say, oh, u is a tan theta. And then du, I'm going to finish it, is a secant squared theta d theta. And the square root of u squared plus a squared. Now, this is again where you've either memorized it, right? You've either memorized this or you can do it algebraically. This turns out to be a secant theta. And now when you rewrite the integral, you get integral 1 over the square root of all this stuff is a secant theta, right? But then you're squaring it. So this is going to be a squared secant squared theta. And then, oh, I forgot my du here, sorry. Du had to be right there. So du would be a secant theta, a secant squared theta. Come on, d theta, like that. With me? Secant squareds cancel. One of the a's cancel. So I can pull a 1 over a out front, and all that's left is 1 d theta. Right, because secant squareds cancel. And the antiderivative of 1 with respect to theta is just theta. So you get 1 over a theta plus c. But what's theta? Go back to this and divide both sides by a, and then take inverse tangent on both sides. And you have theta. And that gets pushed in right there, and then you have the formula. Make sense?
Yeah, that's really cool. Okay, gotcha.
Yeah, it was pretty sick how we
Basically,
just did that.
what's that?
I said it was pretty sick how you just did that.
Yeah, it's just a lot of these formulas, we get them from using the methods that I've shown you, integration by parts, or like the reduction formula that I showed y'all with sine to the n. That reduction formula was integration by parts. A lot of these are done with some technique we've already learned. It's just like, okay, once we know this is the generic formula, then let's just have it as, formula number 17. And there's formula number 18 and 19 and 20, but they're all just some application of something we've learned. So good question. I was wondering if anyone would ask me about that. Okay, let's keep going. So we have this one here, irreducible quadratic. Okay, let me give you another one of these. What if we had, I'm going to make this one up. Let's go with 5 over, let's go 2x squared plus 6. I'm going to make this one ugly as shit, okay? And that way you can, not be afraid of numbers being bad. This is going to be bad. We're going to have all sorts of weird fractions, and it's just going to look weird. All right, so again, you have to get to this point now where you're like, okay, constant over irreducible quadratic, right? Constant over irreducible quadratic. So you're going to have to complete the square on the bottom. So let's go do that over here. 2x squared plus 6x plus 1. First step for completing the square, you always have to make sure that the number in front of the x squared is a 1, which it's not here, right? It's a 2. So I have to factor a 2 out, which isn't so bad on the 6 because I can make that a 3, but it makes the 1 a 1/2. And then you start playing your game. You take the number in front of x, which is 3, right? You take half of that. That's your first number, 3/2. You take that 3/2 and you square it. That's 9/4. That's your second important number. You're going to be adding and subtracting 9/4. So x squared plus 3x. Here comes plus 9/4. Here comes minus 9/4. And then I still have the plus 1/2 here. Okay. And now the first 3 terms are guaranteed to factor to be x. Well, let's put the 2 in front of everything. It'll be in here, x plus 3/2 squared. That's what this is. And then over here, we have to put these 2 together. So I'm going to rewrite this as 2/4. That way I can put them together. And that'll give me negative 7/4. Y'all still good? Now you see this 2 out here? That 2, this whole thing on the bottom is going to get replaced with this, right? So that 2 that's on the bottom, I'm going to bring it out of the integral as a 2 on the bottom, like a 1/2. So watch the way I'm going to rewrite this. The 5 is going to come out. That's the 5 in the top. The 2 is going to come out of the bottom. And then I'm going to have 1 over x plus 3/2 squared minus 7/4 dx. And we have our first slight issue here. Do y'all see that this is a minus and not a plus? Right? This is supposed to look like arctan, like this one, right? Was like something plus 16, something squared plus 16. And we said, oh, that's just formula 17. We're in business. But if it's a minus, that's not the case. So
I have a question.
yeah,
Could you, this might sound silly, but let's give it a shot. Could you, take the, oh, actually, I kind of answered my own question. Never mind.
okay. Were you going to try and take a negative out or something?
Yeah, I was thinking, take the negative out, so you get 7/4. And I was thinking, yeah, I answered my own question. So
Yeah, it'll make the other one negative. So you still won't have what
Yeah.
you need for arctan. However, if you look at your formula sheets, formula 17, where is it? Yeah, okay, so look at formula 17 is what we've been using, right? When you have a squared plus u squared in the denominator, right? See that? But look at number 20. Look at formula 20. 20 is what you have when you have u squared minus a squared. Your variable squared minus your constant squared. And look at 19. 19 is for when it's the other way around. Constant squared minus variable squared. We have in this problem, this one, right? We have this. Let me grab it. So you need to be aware of these formulas because you might run into something like this. The only formulas I would expect you to be aware of are the ones that are on your formula sheets. Okay, I wouldn't expect you to be aware of any formula that's not on your formula sheet. So you need to just know it's there. So do y'all see this is what we have? We have like a u squared minus a squared there. That's this. And again, the u that we have, this u, if we took the derivative of it, we just get a 1 dx. So we don't have to, again, we don't have to scale by anything. And we'll never have to worry about scaling when we complete the square. We would never have to, because we'll always wind up pulling a number out, right? That first step will be pulling that 2 out, and that 2 will just get pulled out of the integral. So we won't ever have to worry about scaling of the u part. So we should just be able to go straight to the answer now. 5 halves out front times, now let's read through this formula. 1 over 2a. Okay, 1 over 2 times a. Now a would be the square root of our constant. So root 7 over 2. All I'm doing is taking the square root of this constant. So square root of 7 on top, square root of 4 is 2. That's 1 over 2a. Understand? Natural log, absolute value, u minus a. Okay, u minus a is going to look terrible. U is x plus 3 halves minus a, which we said is root 7 over 2. And then all of that, same thing, u plus a plus c. And if you're wondering where this formula comes from, it's, again, rewriting this and doing trig sub. It's basically where it comes from. There's some cleaning up that could happen here. These 2's could cancel. I don't know, 5 over 2 root 7. You don't need to rationalize the denominator. It's fine. And then all this again. Make sense? Questions, comments? Okay. Constant over linear. We're in business. It's going to be a natural log. We might have to scale. Constant over linear, repeated linear. Okay, well, that's going to probably be some scaling and some power rule. Constant over quadratic that's missing the x term. It's either formula 17, 19, or 20. Depends on if it's a plus or minus between those, right? This is this here in green, this is a quadratic, right? But it's missing like that, the x term or the u term. And you're either gonna have pluses between those or minuses. And then constant over an irreducible quadratic, we have to complete the square, and then it's gonna be either formula 17, 19, or 20. Good? You sure? Okay. Yeah, all right. This is the one. This is one of my favorite problems in Cal 2 with doing integration, period. I mean, it's just one of my favorite integrals to do, all right? Because there's so many different ways to approach this problem. And I guarantee you that if you go to a tutor, they're going to do it different than what I'm doing here. I can almost guarantee they're going to do it different. And I'm not saying that it's worse or better. I've had a lot of students tell me that they like the way their tutor does it more than they like the way I do it. But there's a reason why I do it the way I do it. I do it this way because I think there's just more critical thinking involved rather than just like robotic steps. All right. So what's the big difference between this and what we did before? Well, we have a linear on top. This is the first example where we have a linear expression on top, right? You see it's linear on top. And the bottom is quadratic and it's irreducible. So this 4x squared minus 4x plus 3 cannot factor. So this is the first time we've run into this. Linear expression on top, irreducible quadratic on the top, or on the bottom. So the way I think about it is this. The denominator is quadratic, right? When you take the derivative of a quadratic, you get a linear expression, don't you? Because the power always comes down by 1, right? Derivative of any quadratic would be linear. So the bottom is quadratic, the top is linear. So in some sense, if I let u be the denominator, right? If u is the denominator and it's quadratic, then when I do du, it'll be linear. And it might be the numerator. Let's just see. So let's just let u be the entire denominator, 4x squared minus 4x plus 3. And let's take the derivative of that, which would give you 8x minus 4 in parentheses dx. Right? Now, wouldn't it be nice if the numerator was 8x minus 4? Wouldn't it be nice? If the numerator was 8x minus 4, then we would have u on the bottom and the derivative of it would be up top, wouldn't it? It's not though, right? The numerator is x minus 1. And I sure wish it was 8x minus 4, right? I sure wish it was. I'm going to make it 8x minus 4. Okay, you ready? This is the part. This is the part that is different. Most tutors and most textbooks, what they do is they complete the square and they do some other stuff, which is fine. But I'm thinking about this like, look, I really want the numerator to be 8x minus 4. So I'm going to force it to happen. Here's what I'm going to do first. It may seem weird, like how are we ever going to get the top to be 8x minus 4, but just watch what I do. Everything is just going to be algebra. So first thing I'm going to look, I wish I had 8x, right? I just wish I had an 8x. So I'm going to multiply by 8 over 8 on the outside of the integral. Right? That's fair. 8 over 8 is 1. I'm allowed to do that. And what I'm going to do is I'm going to pass the 8 through here like that, and then leave the 8 in the denominator on the outside. So this is going to be 1/8 integral, but now it's 8x minus 8 over 4x squared minus 4x plus 3. Are we agreeing that I have not changed the problem at all? Right? I multiplied by 8 over 8. That's fair. That's a legal move. Now, again, I wish it was 8x minus 4. It's 8x minus 8. Right? So now my next kind of clever move. I'm going to go here and write 8x, and I wish it was what? Minus 4? I'm going to subtract and add 4. Now, we still had a minus 8 there, didn't we, on top? And then on the bottom, we have 4x squared minus 4x plus 3 dx. So do we still agree I have not changed the problem? Right? This is the same integral. Now, 1/8 integral. Now, what I'm going to do now is I'm going to split this integral into 2 pieces. I'm going to take these 2 and put them over this denominator, and then split it and put these 2 over this denominator. So split the fraction into 2 fractions. So it becomes like this, or it becomes this. It becomes the 8x minus 4 over the 4x squared minus 4x plus 3. Oh, don't want to close that yet. Hold on. And then plus -4 over 4x squared minus 4x plus 3 dx. Am I allowed to do that? Isn't that the way fractions work? Right? Questions on that? Continuing, 1/8 integral 8x minus 4 over 4x squared minus 4x plus 3 dx. I'm splitting it now into 2 integrals, plus 1/8 integral -4 over 4x squared minus 4x plus 3 dx. Now, the reason I've split it into 2 integrals is because this first integral is easy, right? That's what I was hoping. Remember when I first made this u substitution, I was like, I really wish the numerator was 8x minus 4, because then this integral would have turned into something very simple. U on the bottom and its derivative on top, right? And what is that? What would that become? If the bottom here is u and the top is du, isn't that just 1 over u du, and the
Yeah.
antiderivative is natural log?
Yeah.
Right? Okay, so there's really nothing more to do on this. This is just 1/8 natural log of the denominator.
Then you have a constant over a quadratic on the other one.
Yeah, and now the other one is still here, but now you no longer have linear over irreducible quadratic. You have constant over irreducible quadratic. In fact, I would probably pull that -4 out and just make that a 1. And then reduce that to be -1/2. But see, this is now constant over irreducible quadratic. And how do we handle those?
Complete the square on the bottom.
The square, okay? So we still have more work to do. I'm gonna keep working, but I just, again, want you to appreciate that the reason, again, I like this method is because it forces you to make something happen algebraically that you want to happen. And I think that that's just a better way to, I guess, learn. Just for me, I think people's brains working that way is better than you just doing something more mechanical without really knowing why you're doing it. So anyway, all right, so let's continue this one. So this part of the problem's done. Now this part, I'm gonna just kind of go over here and let me do a completing of the square. I gotta pull a 4 out first. X squared minus 1x plus 3/4. Okay, 4 here. All right, look at the number in front of the x, which is a -1, and I take half of it. All right, so I'll do that up here. I take -1, half of it. That's my first number. I take that number squared, I get 1/4. That's my second number. And then I rewrite this x squared minus x. Here comes my adding of a 1/4 and subtracting of a 1/4. And I already had a 3/4 here. And then here, still my 4 out here, that breaks down to be the x minus a half squared. And then when I put minus 1/4 and 3/4 together, I get 2/4, which is a half. That.
Sorry, I got lost. Where was the -1/2? Where did that?
For completing the square, we always take the number in front of x,
Oh, okay,
right?
I saw. Okay, I see.
And then
I was,
half of it.
yeah, I was looking at -4. Okay, my bad.
Okay, yeah, and remember, because we had to pull that 4 out to start the completing of the square. All right, now this 4, when I redo this integral, this 4 is going to come out on the bottom, isn't it? It'll come out on the bottom, and it's going to join with these. So why don't we just leave that the way it is? It's -4/8, but I'm bringing a 1/4 out because of the 4 on the bottom there. I have an 1 over, and now I have x minus a half squared plus a half dx. And if we squint our eyes appropriately, this is formula 17, isn't it? Formula 17. So I've got here minus 1/8. Okay, that comes from here, those two together, right? Minus 1/8. And then a here, right? A in this problem is the square root of 1/2. Right, that's what a is. A is square root of 1/2. So the square root of that would be 1/√2. If I took the square root, that's what a is. And now I'm using formula number 17. So formula 17 is 1/a inverse tangent of u, but for us, u is the x minus a half over a, which is 1/√2 plus c. So our final result is this. Let's see, minus, I'm going to just reciprocate this 1/1/√2. I'm put the √2 on top. So this will just be √2/8 inverse tangent of On this one, I'll just leave it. Who cares? It's all right. If you go and do your homework, most of the time, the book is going to rationalize denominators and clean things up algebraically, and it will look different than yours. But this is all I expect from you, like on a test. Just get it here. We're happy. Okay. It's a lot of work, huh? A lot of work.
It's not much more than the last ones we were doing in the last chapter.
Yeah. Okay, so I'm curious here. I'm gonna go to Wolfram. I want to see what Wolfram gives us on this one. So we want to integrate. It was x minus 1, right, over 4x squared minus 4x, was it plus 3, I believe?
Yeah, +3.
Okay, let's see what we got here. Well, this is it right here. So now they use log instead of natural log. In Wolfram, it's log is natural log, which is weird, I know. Let's not think about that too much right now. So 1/8 natural log of this. That's what we got, right? That first part, we got what's going on here? We got 1/8 natural log of all that stuff. Okay, we got that. And then if you distribute this 1/8 through here, you'll get -√2/8 inverse tangent of this. Now this, like I said, they did some work here. All they did was multiply the top and bottom by 2. And they rewrote this, they rewrote that instead of like that, they wrote it as √2/2. So they rationalized the denominator. And then they multiplied through by 2 on the top and bottom. So they got 2x minus 1, and then these twos cancel, so you just get √2 on the bottom. That's what they did. Okay. All right. How are we feeling? Constant over linear, it's going to be a natural log, we might have to scale. Constant over repeated linear, might have to scale power rule. Constant over quadratic with no x term, it's going to be like formula 17 or 19 or 20. Constant over irreducible quadratic, complete the square, right? Linear over irreducible quadratic, play this game, right? Play this game where you let u be the bottom, du, right, is whatever it is, and then you just try and make the top look like that, where you wind up splitting things apart. And when you do this, guaranteed, you're always going to get 2 integrals. The first one will be easy. The second one, you'll have to go and complete the square. What's next then? Linear on top, right? That's a linear on top. And that's a repeated irreducible quadratic. Now, it may not look like it, but x squared plus 1 is irreducible. Like you can't factor it. If it was x squared minus 1, right? If it was x squared minus 1, you could do difference of squares, but x squared plus 1 does not factor. So that, in fact, is an irreducible quadratic. And we cannot use formula 17 here because formula 17 does not account for that, right? And also formula 17, on formula 17, you don't have a constant, I mean, you have a constant on top, not a linear, right? Here we have a linear on top. All right, well, I'm gonna play the same game. I'm gonna let u be the bottom, x squared plus 1, okay, just the quadratic part. The derivative of this is 2x dx, right? Okay. I sure wish that the numerator, was 2x, but it's not, right? It's not 2x. It's x plus 1. Well, that's okay, because I'm going to make it 2x. I'm going to just take this integral, x plus 1 over x squared plus 1 squared dx. I'm going to multiply top and bottom by what?
2/2.
2/2. And that 2 must distribute. So now we're going to have integral, oops, 1/2. I had the 2 out here on the bottom. The 2 on top goes through, so 2x plus 2 over. And now here we have x squared plus 1 squared dx. Remember, I wanted 2x, right? I wanted 2x on top. I have 2x plus 2. So right now, all I have to do is split this into 2 integrals. I can do 1/2 integral 2x over x squared plus 1 squared dx. And then the other one plus 1/2 integral 2 over x squared plus 1 squared dx. Any ideas on how to handle the first one?
We just use our U sub and then becomes 1/U squared.
Yeah, just using that u sub for this one. Du is on top, right? 2x dx is exactly the top. That's du. X squared plus 1 is u. So this integral really looks a lot like 1/u squared, doesn't it? 1/u squared. And then that we could use power rule on. So
-1/2 U squared. U to the -1.
yeah, I'm going to go 1/2 comes out. And then because I'm doing the antiderivative of u to the -2, it'll become 1/(-1) u, which is x squared plus 1 to the -1. That's me doing like a mental u substitution and antiderivative of this. You okay with that? I'm going to take the second one to a new page. Okay, so I'm putting you in breakout rooms and I want to give you about 5 minutes to see if y'all can attack that one together. What I really want you to do is talk about how y'all are going to go about it. Okay, so I want to see if any groups can get it. Okay, I think everybody's back. So how about room one? Caitlin, Lauren, Lewis, and Ricardo. Did y'all come up with a way to go about it?
Well, we thought we did,
What did
but
you do?
we ended up doing something else. Well, I ended up doing something else.
What did y'all
Um,
do?
So what I did was I took the 2 out and it became 2/2, so that was the 1. And we just had a 1 on top.
Okay,
Then I was like, oh, that's a simple U sub. And it ended up being 1/2 du equals x dx, and I didn't see the x. So that's when I stopped and realized I was wrong.
yeah, you can't do a basic U sub here because if you use the substitution x squared plus 1, you need a 2x somewhere. You don't have a 2x. So, yeah,
So what the answer is like, we're supposed to do the first step that Ricardo said, that's cool. Then we're supposed to multiply out the x squared plus 1 times x squared plus 1, complete the square, and then insert our inverse tangent formula.
Question,
Okay.
shouldn't it be a 2 on top?
yeah, but there was a 1/2 and then they said, Lewis said to just pull the 2 out, so. Okay, so wait, Lewis, what did you say? I didn't follow you there.
So sorry about that. My mic is a little bit rough. So again, we took out the 2, right? Now we
Okay.
got we got x squared plus 1 squared. We need to complete the square. So what we do is we multiply x squared plus 1 times x squared plus 1.
Oh, so you actually squared it out like this?
Yeah, what I'm thinking to do is that, and then we complete the square from there. Oh, well, it's already completed.
Yeah, see, it's already
Plus 0.
completed. X squared plus 1 is already a completed square.
Okay, so we got x squared plus 1 plus 0, which is this going to be 0?
Yeah, completing the square is not going to go here. All right, so look, let me skip. Let me go to room 5. Let me try room 5, since y'all thought I wasn't going to call on you. Alec, Jonathan, Mohammed, did y'all get anything?
No, we did the same thing as the first group.
Okay.
I had 2 ideas.
Okay, let's see, Joshua. What did you do, Joshua? Or what?
Hello.
Yeah.
Well, at first I know you said not to do a basic U sub. I did do a basic U sub first, and I got negative 1/2 times x squared plus 1 plus c. The second option I was going to do that I just ran out of time was to do if you factor that out. Oh wait, actually, no. Actually. Well, but the second thing was I was thinking it might be an irreducible quadratic that you could divide, you could take the derivative of. But that was my only other thought.
Okay. Not sure that's going to go. Did anyone have some other way?
So I had a thought like pretty shortly. I didn't get a whole lot of chance to properly go over it. But if you just treated it as if, you know, it was a fresh problem, I guess, and took it like you were going to do U sub, you'd find that you could get du equaling 2x dx. And then I thought, well, what if I multiplied the whole thing over x by x over x? And then I could factor an x in at the beginning on top. I could multiply that in. So I'd have 2x over x squared plus 1 squared, which I could U sub that.
Okay, so everyone seems to be married to this U sub idea. Let's just see why it's not going to work. Okay, so let me try and follow you here. You said, okay, you don't have 2x, so you divided both sides by x. Is that my understanding, to get rid of that x?
No, I
No?
multiplied the integral by x over x.
Outside the integral?
Mhm.
Okay, that can't be done.
Why not?
And the reason why is because you're multiplying by a variable, right? As opposed to a constant. Remember, constants can come in and out. But when you put variables in, even if it's x over x, you can't put this x in and leave this x out. Now, what you could do is you could put an x over x in here, but this x on the bottom has to be there as well.
Gotcha, which would interfere again.
which would interfere with the stuff on the bottom.
Gotcha. Well, thought it was a little too easy.
Okay, no, this is why I wanted y'all to work this, because what I want you to see is that, like, even though I'm trying to give you like kind of templates in terms of how to attack an integral, even if I give you those, you may have something within that integral turn out to be something really weird, okay, and really different. So anyone else have, before I show you?
I have one last idea.
Okay,
I'm probably wrong, but it's totally cool. Could you multiply by the reciprocal and do x minus 1 over x minus 1 times the integral?
you can't do that on the outside, no.
You're right.
You can only multiply by constants. You can only do like, 2 over 2 or 5 over 5 or -10 over -10, but you can't do any variables on the outside. And if you do the variables on the inside, like x over x or x minus 1 over x minus 1, then everything else gets thrown off. So watch, I mean, I think when I show it to you, I think you're not going to be that surprised. You're just going to be like, oh, I just didn't think of it that way. I'm going to rewrite the bottom as the square root of x squared plus 1 to the 4th power. And then I'm going to use trig sub. Okay, that's what I'm going to do. Right, because I really don't have much of anything else. Okay, I really don't have much of anything else. So the trig sub I'm going to use here, I'd have to go back to last class. I'm going to replace x with a tan theta. Right, that was our trig sub. So this will just become tan theta. Dx will become secant squared theta d theta. And then the square root part will turn into just secant theta. Y'all understand what I'm doing here?
Yes, I did not even think about that.
Yeah. But now you know, right? Now you know. And what would have let you know this? What lets you know it is that the basic U sub's not going to work, right? Basic U sub's not going to work. And then the other thing that lets you know to do this is that that's squared there, right? Look, if that squared wasn't there, this is formula 17, isn't it? But because the squared's there, you're not going to be able to get around that. By the way, I should mention this. This does not become this. I've seen this happen on tests, and I always feel bad when I take off a bunch of points. I've seen students split it up into 2 pieces like this, because that's what it means on the bottom to square it, right? And then they just give me arctan for each one of those. And that's wrong, because this is a product and you can't split up a product this way. So don't do that. Okay. Okay, so I'm back here. So this integral now becomes, let's see, 1 over, okay, the square root thing here is secant, right? And I'm going to have it to the 4th power. So secant to the 4th power theta. And then dx is secant squared theta, d theta. Y'all follow it? That's going to turn out to be 1 over secant squared, isn't it? 1 over secant squared. But 1 over secant squared is really what?
Cosine squared.
Cosine squared. And we know how to do cosine squared, right? We just power reduce it. So this becomes integral 1/2 1 plus cosine 2 theta d theta. This look familiar? I hope this looks familiar. This was 2 classes ago. From here to here. Pull the 1/2 out. Let's see. Let's do the antiderivative. Theta. And then we've done this antiderivative so many times. That's just 1/2 sine 2 theta plus c. And we've had to deal with this sine 2 theta several times now, right? We have to use that double angle identity. So this becomes 1/2 theta plus, well, this turns into 2 sine theta cosine theta, and then the 2 1/2 cancel. So this just becomes sine theta cosine theta plus c. And now I just need to know what theta is, sine theta and cosine theta. So I go back to my trig sub, which was up here. It was X was tan theta. I draw a reference triangle. X over 1, square root of x squared plus 1. And now I've got sine, cosine, and I can get theta from this, right? Just take arctan on both sides. So I think we're here. 1/2 theta is inverse tangent of x plus sine of theta, which is opposite of our hypotenuse, x over square root of x squared plus 1, times cosine theta, which is 1 over square root of x squared plus 1, plus c.
Now, we just got to the point where it was 1/2 times theta plus sine theta cosine theta. Would that be an acceptable answer? Or would you want us to simplify it further?
You mean leave it in terms of theta? Or get it in terms of x and leave it like that?
In terms of theta.
Nope, you got to go back to x.
Oh, okay.
You have to go back. Think about the original problem, right? The original problem was in terms of x. So your final answer needs to be in terms of x.
Oh, okay. I see.
It'd kind of be like me asking you, like, what's your favorite color? And you tell me German Shepherd, right? I mean, it's x and, you know what I'm saying? Like theta and x aren't the same thing. We're not talking about the same variable anymore. So we have to get it back to the original variable, because you might be 3 variables away from where you started, right? You might have done a U sub, then you might have done a trig sub. And so theta may be very disconnected from x. So you got to get it all back to x.
Are you not a fan of German Shepherds?
That's the first dog I could think of.
Thank you.
Okay, this is not our final answer, right? Because remember, this was the second integral. We had split this up on an earlier page, didn't we? Hadn't we done this? I've forgotten. I've lost it. Where is it? Where the hell is it? Oh, it was, yeah, it was this one, right? Remember? The first thing I did is I did do a U sub. And then I tried to make the top look like the bottom. I mean, sorry, the top, I tried to make the top look like the derivative. So I needed a 2. So I put a 2 over 2, and I slid the 2 in. Then I split this into 2 integrals. And this integral you all said was pretty straightforward. And then this one obviously turned out to be a bit of a nightmare. But this right here, we had the answer for. Here was it. This is it right here, right? So I think I'm ready to put the final answer together. It's going to be that answer plus, okay, what we just got for this answer, right? Which was way over here somewhere. Here, this is it. Right there. I can take the equals out of there. Just leave as a plus. There we go. That's the answer. Now, there are different ways of, you could have maybe done this a different way, okay? I don't know, maybe there's a more efficient way to do it. This seemed to me this path that got us there, right? Curious, let's look at Wolfram. Let's see what it does. It was x plus 1 over x squared plus 1, that quantity squared. Let's just see how much our answer looks like theirs. Wow, doesn't look like it at all, does it? Well, yeah, maybe there's some simplification we could do to ours. Yeah, we could, you know what we could do, because this is really 1 over x squared plus 1. We could put these two terms together with a common denominator, right? Yeah, we just put those two together with a common denominator. I think we're good. So, all right. All right, so we have now covered the 8 problems to get us ready for partial fractions, right? So at this point, now we're going to talk about partial fractions. And when we do these problems, most of them are going to turn out being like we're gonna break something up into a bunch of parts, and each of those parts is gonna turn out being like something that we just looked at. And so you'll have to, chip away at each piece. So what is partial fractions? I thought about all the different ways I could, remind you of what partial fractions is. In my notes, I have like the formal actual breakdown of partial fractions. First thing you have to know is that we do partial fractions on rational functions, and a rational function is just a polynomial divided by a polynomial. So these are examples of rational functions. All of these are rational functions. And yes, we are going to find the antiderivatives of all of these, all right? And they look horrible right now, and I agree, those look terrible, but we're going to be able to find the antiderivatives of those. Not yet. So here's the strategy on how to do rational strategy for how to integrate rational functions. And I'll get to this strategy, but it talks about partial fraction decomposition. Here are my notes for it. Notes are always so hard to read for partial fractions. So I just want to kind of take you back and just get to what is the basic idea of partial fractions? The basic idea is that you start with some expression where you have a polynomial divided by a polynomial. Now, for these examples, I'm going to use a very simple numerator. I'm just going to use 1 for all of these. But just imagine those ones could be some complicated polynomial expression. The idea of partial fractions is that you want to take this big complicated expression and break it into smaller pieces. And then each one of those we will try and integrate. So instead of trying to integrate this monster, we do partial fraction decomposition and then try and integrate each of the smaller pieces one by one. And we can do that because there's pluses and minuses between these. The technique though is, the question is, how do you go from here to here? That's what partial fraction decomposition is about. So the general idea is this: if you start with a rational function, you look at the denominator and you factor it completely. Okay, so you have to completely factor the denominator, which I've already done here for us. That is a completely factored denominator. And what I do is I look at each of the factors. And in this case, I have 3 factors. X plus 4, that's one factor. X minus 5, that's the second factor. X plus 1 is the third factor. Those are all different factors, right? In other words, if I plug in, if I plug in -4, it'll make this 0, but it won't make the other 0. If I plug in 5, it'll make this 0, but it won't make the other 0. If I plug in -1, it'll make this one 0, but it won't make the other one 0. So they are distinct linear factors. Anytime you do partial fractions, what you're going to do is you're going to take this, if for each distinct linear factor, you put a generic letter, A, over the first linear factor, B over the second linear factor, and then C over the third linear factor. And then your goal at this point is to figure out what A, B, and C are. You have to go find out what those are, which I will show you how to do it, okay? I'm just trying to remind you what the technique is. Now, if you have a linear factor that's squared, we call that a repeated linear factor. Here I gave you x minus 4 squared, here's x minus 5 cubed. These are both repeated linear factors. The way you break down a repeated linear factor is you first put a letter, generic letter, over the linear factor to the first power, and then you do another letter over the linear factor squared. So since this was squared, I stop when I get to squared. For the other linear factor, I have a cubed. So what I do is I put a letter over that linear factor, then another letter over that linear factor squared, and then another letter over that linear factor cubed. And that's where I stop. I stop when it gets to 3. If that had been a 4, I would do another letter over x minus 5 to the 4th. Does this ring a bell at all? A little bit?
Yeah, I remember this stuff pretty distantly.
Okay. Now look at this last example I had, or second to last example. Here I have a distinct linear factor, x plus 4. So I know, okay, I'm going to need a generic letter over that. Okay, got it, got it, got it. All right, now the other one, x squared plus 9, is an irreducible quadratic. X squared plus 9 does not factor. And anytime you have an irreducible quadratic, you have to do something special. You have to put not a generic letter over the irreducible quadratic. you have to put a linear expression over the quadratic. A linear expression, bx plus c, on top of that irreducible quadratic. That's the way we handle irreducible quadratics. So if it's a linear factor, you put just a generic letter over the linear. But if it's an irreducible, you put a linear over the irreducible. And then here's kind of like that kind of couple of things happening. We have a repeated linear factor, right? It's squared. So I need to do a over this, then a b over that squared, and that's where I stop. And then this is an irreducible quadratic repeated, it's squared. So because it's irreducible quadratic, I have to put a linear expression over the irreducible quadratic, then another linear expression over the irreducible quadratic, but this time squared. And if it was cubed, I would do another linear expression on top over the irreducible quadratic cubed. All right, I hope this kind of gets at least some of the brain going. Let's do an actual example, like a real example, and then maybe this will start to come together slowly for you. Let's take, let's see which one I want to do. Let's do this one right here. Let's do this one. I'll get back to F. Let's do this one. What I want us to do is let's first just practice the partial fractions on this. All right, let's just do partial fractions on this. So what I'm going to do first is I'm going to factor the denominator. And if you want, you can factor the numerator. You don't have to. But I'm going to factor the denominator here. Now, first I see that there's a GCF. I can pull an X out. All right, so I can pull an X out of the bottom. And then 2x squared plus 3x minus 2, that factors. And if you don't know how to factor that, this is going to be problematic, isn't it? If you're not sure how to factor that. But I hope you would agree with me that I should expect that a Cal 2 student can factor a trinomial at this point. So let me just double check. 2x squared plus 4x minus x, that's 3x, and then minus 2. Okay, so that's my factoring. All right. I have three distinct linear factors. They are x, 2x minus 1, and x plus 2. Three distinct linear factors. None of them are repeated. So this should be a relatively simple breakdown. This should be some number, which I need to go find, a over x, plus some other number, b, over 2x minus 1. And then finally, some other number, I don't know, over x plus 2. And now what I need to do is go find a, b, and c. Because don't you all agree that if I knew what a, b, and c are, this would be a very simple thing to integrate, right? If we actually wanted the integral here, instead of doing the integral of the left side, we just do the integral of the right side. And this would be easy because this is constant over linear, constant over linear, constant over linear. We should get 3 natural logs there, shouldn't we? It was like the first thing we talked about today. Okay, so how do you go about this? Well, anyone remember how to do this? How to figure out what A, B, and C are? What my next step is?
Insert your zeros,
Sorry?
insert your zeros, and then like find that from 1.
Insert your zeros. I think I know what you're saying. I think I know what you're trying to say, but it's not, we don't do that yet. We want to clear the fractions. That's what we want to do right now. We want to take this expression and we want to multiply the left side of this by the denominator. And then we take all of this and multiply it also by the denominator. Now, on the left side, these denominators, or this numerator here, that cancels. So all you're left with on the left side is x squared plus 2x minus 1, right? Just the numerator, that's the only thing left on the left side. With me? On the right side, you have to take this entire expression and distribute it here and here and here. And when you do the first one, right, when we do this first multiplication and it multiplies, we have an X on the bottom, right? So it's going to kill off the X here, but it's not going to kill off the other two. So we'll still have an A there. We'll have the 2x minus 1, and we'll have the x plus 2. Then when we do the second multiplication, we'll distribute through, and this time the 2x minus 1 is on the bottom. It will kill off this 2x minus 1, but we'll still have the x and the x plus 2 and the b. So this will be plus b. We still have the x, and then we have the x plus 2. And then we do our third multiplication. And when we do that here to here, the x plus 2's cancel this time, which leaves us with a c, an x, and a 2x minus 1. Questions on that? Remember, our goal is to find A, B, and C. That's our goal. So what we do now, we really have two choices. At this point, we have two choices. We have the short way and the long way. The short way is great because it's short, but it doesn't always work, especially when you have irreducible quadratics, which we don't have here. The short way is nice when there aren't irreducible quadratics, nice and fast. The long way is, well, long, but it works no matter what. Okay, so I'm going to show you both ways. So first, I'm gonna do the short way. The short way of doing this is to look at this thing. We're trying to solve for A, B, and C, right? We're going to look at this, and what we're going to say is, let's first try and find A, okay? Let's try and find A. So if we're going to find out what A is, what I'm going to do here is I'm going to look at these two terms, the ones that don't have A, and I'm going to start thinking, what X value could I plug in there that would kill these off and leave this one unchanged? What value of X would kill this and this off and not kill this off? If X was what value?
0.
0, right? Everyone see that? If I put X to be 0 here, it'll kill this, and it'll kill this, but it will not kill this. So what I'm going to do now is I'm going to say, all right, let's let X be 0. And when I say that, what I mean is let X be 0 on the entire expression. Replace all your X's with 0. So the left side of this becomes 0 squared plus 2 times 0 minus 1. So the left side is -1. Everyone understand? I'm just plugging 0 into the left side for X. On the right-hand side, I get A.
Sorry about that. Isn't there an integral still there? Like,
I haven't done any integral right now.
so like in theory, these are all like integrals of each one. We're just,
Well,
so
they
we're just
will be.
manipulating.
They will be integrals. Right now, I'm not doing any calculus. This is just purely algebra. If
Yeah.
we start with this expression right here, right? If I start with this, is there a way you can break it down into this thing we call the partial fraction decomposition? Once we do that, then we can go do the integral. So I'm replacing X with 0, I get -1. Let's see, if I plug 0 in here, 2 times 0 is 0. If I take away 1, I get -1. And then 0 plus 2 is 2. And then the rest of these are gone, aren't they? These two are gone? Because I'll get 0 plus 0, so that's there's nothing left there. And if we simplify this, we get -1 equals -2a, which means that a has to be a half. Divide both sides by -2. You understand? Let's find B. So to find B, by the way, when I took Cal 2, my professor just went straight from this step to this step with A, B, and C already given to me, and it was left to me to figure out how to do that. So, you know, the expectation here is that you can do this. I'm running through it again because I'm practical. I realize people haven't seen this since pre-cal, maybe, you know, so there's a lot here, but okay, we keep going. Find B. So if I want to find B, I want to kill off A and C. I want to kill off these two. So what number would I plug in for X to kill off this piece and this piece?
1/2.
A half. X would have to be a half. Right? Y'all see that? You plug in 1/2 right here. You're basically saying, what you're basically doing is saying, if you're trying to find B, you're looking at the other two and seeing what those two have in common that this one doesn't have, right? This has a 2x minus 1, this has a 2x minus 1, this one doesn't. So what makes 2x minus 1 equal 0? Well, just solve it. 2x minus 1 equals 0, you get x is a half. So that's how we're picking a half. So we're going to let x be a half. And we're going to plug it into everything, this equation, everything. So a half squared is a fourth plus 2 times a half minus 1. So that's the left side equals. Now I know when I plug in a half into this green one, it's gone. When I plug in a half into this green one, it's gone. So the only thing I really have to do is plug in a half right there for x. So b times a half. B times a half times a half plus 2. Let's see, my left side is 1/4. That's one. Oh, that's all, just 1/4, because this is a 2, half of 2 is 1, 1 minus 1 is 0. So 1/4 equals, let's see, b times a half. And then in there, I get half plus 2 is 2.5. That's 5 halves. So 1/4 equals, let's see, if we multiply across here, we get 5/4 b, and then I can multiply both sides by the reciprocal, and you should just get 1/5 for b. And then we find c. What are we going to plug in for x to find c?
-2.
Yeah, we're going to be looking to see what makes this guy and this guy go away, right? So x would have to be -2 here. And then we rewrite everything. So we get -2 squared, that's 4 plus 2 times -2 minus 1 equals, okay, we've killed off these two. So all I have to do is plug -2 in there next to the c. Let's see, we've got these four, the 4 and the -4 cancel, so I get -1 on the left again. Over here, I get c times -2, and then -2 times 2 is -4 minus 1 is -5. So we get -1 equals 10c. So c is -1/10. All right. All right, we're there. We know A is a half, B is a fifth, C is a tenth, -1/10. Which means if I go back up to this step right here, remember we said that this was going to turn into some number over, what was it, x, plus some other number over 2x minus 1, plus some other number over x plus 2. We found those numbers to be A, which is a half, it was a half over x, plus B, which was a fifth over 2x minus 1, and then the last one was -1/10 over x plus 2. Go with me? Okay, now. What if we wanted now to do the integral of x squared plus 2x minus 1 over, let's see, 2x cubed plus 3x squared minus 2x. 2x cubed plus 3x squared minus x dx. Let me just double check that is what we had, right? minus 2x. Okay, so what if we now wanted the integral of this? Well, we would first eliminate all the things we have, right? Like this is not a basic U sub. This is not integration by parts. This is not trigonometric substitution, right? All these things that we've learned, none of them work. This is a rational function. So I'm going to try partial fraction decomposition. So I'm going to break this down to be 1/2 over x plus 1/5 over 2x minus 1 plus negative 1/10 over x plus 2 dx. So this step right here is your partial fraction decomposition that we just did. And now each of those we should be able to handle because this is a constant over linear, constant over linear, constant over linear, right? So let me try and do each one of these now. Okay, the 1/2 up top, don't let it freak you out. It's just a 1/2, just a constant. Let's just bring it for the ride here, 1/2. That really looks to me now like a 1 over x, and the antiderivative of that should just be natural log absolute value of x. Next one, plus, okay, the 1/5 is a constant, times. Uh-oh, this time my linear on the bottom is 2x minus 1, which means I'm going to need to scale the 2, right? So I'm going to have to put a 1/2 out here, and then I'll have the natural log of 2x minus 1. And then on the next one, I have that negative 1/10, so I'm going to bring it out front as negative 1/10. And then this one, I do not have to scale because there's a 1 in front of that x. So this will be natural log of x plus 2. Plus c, we're done. Is that class? Are we done? We're done. Shit. Okay.
Yeah, we are.
Yeah. So, man, as far as homework is concerned, we really don't have any problems that we are theoretically ready for. So
That's good. I still got leftovers from last week.
yeah. So yeah, maybe we should just take some time to get caught up on other things. If you absolutely have nothing to do, maybe, you know, you could just do something like practice. I would practice a couple of these where you have like a linear expression, maybe like, you know, x plus 4 over some irreducible quadratic like x squared plus 5x plus 2 dx. Like, see if you can find the integral of that. Or yeah, or just do it with, well, I mean, that's a pretty long problem because there's a lot to do with that. That's kind of like what we did. Well, very close to what we did. What was it? This one right here. Right. I feel like if you can do one of these, then you're pretty much there in terms of like ready to move into the rest of this. Also, the other thing I would ask you to go back and review if you have time. Review log division. And if you can, synthetic division. So how do we do this? We're going to have to do long division, synthetic division. So the way these problems are going to work is that you're going to get an integral that's going to be something like, let's see, something like e right here, where you're going to first start this off with long division. After you do long division, then you're going to have to do partial fraction decomposition. After you do partial fraction decomposition, the remaining integrals are going to fall into different categories. Some of them are going to be easy, like the ones we just did, natural log, and some of them are going to be hard, like a linear over an irreducible quadratic, which is going to take a bunch of steps. So, you know, in theory, this problems could take you half an hour, 40 minutes to do just one of them. So All right, we're good. We'll call it a day. Get caught up on everything. Don't try any homework from 6-3 yet. Have a good one.
Thank you, sir. Have a nice rest of your day.
You as well.
Keep up the cardio, sir.
Yes, sir. Plan on it.
Nice day.